Okay, so today we're going to make the full-blown change out of one-dimensional symmetry and into three-dimensional symmetry. We're going to look at assigning point groups. So we're going to work with the flowchart, which I'll pass out in a second, and we'll go through all of the different kinds of point groups that we'll encounter in this course. And then we'll see the power of that by assigning our symmetry selection rules for the 1D particle in a box using the character tables and the direct product table. So we'll go through all of the symmetry analysis in just this one lecture in kind of an abbreviated form. And if there's time, we'll take a Kahoot. Okay, so point groups. This idea of a point group, if I could get some help maybe passing these out, you can see that there's the endpoints on this flowchart are the point groups. So you should have lots of extras, so if you don't mind, recruit some help. The point, that word point stands for the single point of symmetry, which in all of our molecules is going to be the center of the molecule, the center of mass of the molecule. You do not have to have an atom at the origin. Think about benzene. Right, the center of mass of benzene is right in the middle of the ring. There's no atom there. So there's no atom that's the point of a point group. It's the origin or the center of mass. The group part is a group of symmetry elements. And when you have the group of symmetry elements, you're going to have different types of molecules. If you think about benzene, it's got a planar structure. It's a six-fold symmetry molecule. That's going to be different than, say, methane, which is a tetrahedral structure. So years ago, they came up with this notation, this Schonflies notation, which is the point group label. And we'll get very familiar with those today. And so this, we're going to use the flowchart that is being passed out right now to find the point group of a molecule. So let's look at, I'll walk through a flowchart similar to this, thanks. And then we'll go practice on the Schonflies notation point group on Symmetry. Okay, so here's a generic sort of way of looking at these molecules, this point group identification flowchart. In your notes here, I've got an example of every type of molecule. And so you have the very first question. Sometimes the question on Symmetry is listed as, are there any C infinity axes? Well, the only way you're going to have a C infinity axis is to have like a perfect ring or a linear molecule. Since we have discrete atoms, we'll never get a perfect ring out of a molecular system, but we will get a linear molecule. And so that's another way to ask that same question, is the molecule linear? So it splits off the linear molecules first. So these are the only two linear molecules. Molecules that are symmetric, in other words, have an inversion center, and molecules that don't. If they do have an inversion center, then this is the point group of the molecule. So we arrive at the endpoint, and that's when we say, what is the point group of CO2? It's D infinity H. Something like, say, carbon monoxide, where it's still a linear molecule, but they're not the same atom, that would be C infinity V. So these squares are the point groups. And that's the Schonflies notation. The I? The inversion. Does it have an inversion? And so if you're looking at CO2, obviously the oxygens on opposite sides can invert into each other. And I don't know what this molecule is, maybe OCS. But anyway, the end atoms are different, and so then there's no inversion. So that would be a C infinity V. Your homonuclear diatomics are on this side, like N2 and O2, H2. And then all of your heteronuclear diatomics are over on this side, like CO and HCl, etc. All of those diatomics have to be linear because 2 points define a line. And so all your linear molecules are, all your diatomics that are either homonuclear or heteronuclear, they're all either D infinity H if they're homonuclear or C infinity V if they're heteronuclear. So you know right away HCl is C infinity V and N2 is D infinity H. Okay, if it's not linear, then you're done with those 2-point groups and you have to move down through the table. So you say no to this. All the diamonds, if you're not familiar with flowchart terminology, the diamonds are decision boxes. The squares are endpoints. So you have a decision box, yes or no question. You say no, you go to this diamond. Are there 2 or more unique C3 axes? And so this is looking for highly symmetric molecules, like these 3 down here, a tetrahedron, an octahedron, or a icosahedron. There may be more, but these are the 3 common ones. Tetrahedral and octahedral are the most common of the highly symmetric ones. So if we're looking at this methane, right, we have this CH axis, and it has 3-fold symmetry. 1, 2, 3. So I can spin it around that top hydrogen and have 3 rotations. Okay, but I could have just as easily picked this hydrogen coming out of the board, and it has 3-fold symmetry. So every one of those CH bonds is a unique C3 axis. So that's why we would have said yes. If we had methane, we would have gotten to this box, 2 or more unique C3 axes, I would say yes. So I would jump over here. Then it asks, is there an inversion center? And I would say no, because this top hydrogen here, if I invert through the center of mass, there's nothing down here for it. So there has to be a hydrogen on the other side for it to have an inversion center. So inversion, everything goes through the center of mass. And so like this number 3 here would go through that carbon and hit this side, but there's no hydrogen over there. Okay, so it does not have an inversion center. So if it has lots of C3 axes but no inversion center, it's a tetrahedral molecule. And that really helps if you've got a really complicated molecule like, let's see, is it tetramethylsilane. So you have 4 methyl groups on a silicon. The TMS, we use it as an NMR standard, right? It's take that methane and put 4 methyl groups on there. So now you have lots of hydrogen sticking off in all directions. You still have 4 C3 axes and no inversion center. And so that molecule is going to be tetrahedral as well, even though it's really complicated. And we'll see that in the flowchart. We'll look at that one. If it does have an inversion center, then you're over here, and it's asking, does it have 5-fold symmetry? This is a C5 axis. Okay, so 5-fold symmetry question. An icosahedron has 5-fold symmetry, an octahedron does not. Okay, and so it's really just deciding between a icosahedron or an octahedron. And so this is the flow chart. This is how you go through the flow chart. I'll show you the next one. So here's lots of more questions. But what we'll do is we'll go ahead and go through the flow chart using SymOtter. But here you have examples of molecules in each different type of point group, all on one page here. But let's go ahead and practice with the SymOtter webpage. So I'm going to flip over to the browser. Okay. And so first we need to pick a molecule. Let's pick ammonia. Let's start with something kind of easy. Okay. Now it's shown this way, but I'm going to rotate it around to where we would typically draw it. Like we would typically draw ammonia like this, with a nitrogen and a hydrogen, and then a wedged hydrogen coming out front and a dashed hydrogen going in the back. And so that would be how we would typically draw ammonia. And so this is the first question in our flowchart. Does this molecule have an infinite rotation axis, a C infinity axis? No, it doesn't. It would be a C infinity axis would be I rotate it 1/infinitieth of a turn, right? That's that little lowercase n, the Cn, is how you divide the 360 degrees. So you're dividing by 3 for a C3 axis, you're dividing by 4 for a C4 axis. Here you're dividing by infinity. So only linear molecules are going to be able to do that. You rotate it 1 infinitesimal degree and it still looks the same. Can't do that with ammonia. So I'm going to say no. Does this molecule contain 2 or more unique C3 axes? Well, it's got 1, but that's it. So like if I drew the NH axis, it doesn't have a C3 axis. But going through the nitrogen, top down, it does have one, but that's not two or more. So I'm going to say no. So then select the highest order proper rotation axis if there are any present. And so I'm looking at this, I see a C3 axis, so I'm going to pick a C3. So I'm going to come in here and do 3. Okay. So I'm looking at that axis that comes through the nitrogen, and I'm going to hit select. They've added some extra features to this flowchart. Are there 3 C2 axes perpendicular to this highest order axis? This is the square or the diamond on your little flowchart that confuses people the most. What you're trying to do is you pick the axis that has the highest order. So if it's a 4-fold molecule and you have some C2s next to it, you pick the 4-fold one. So you pick that C4, and then you're looking 90 degrees. Is there a C2 90 degrees to the C4? And we picked a C3 going up and down, but there are no C2s 90 degrees to that. So we're going to say no. We'll do another molecule where that will be yes, and it'll be a lot easier to see. Okay, so then does the molecule contain a horizontal reflection plane? If this is my symmetric axis, the C3 axis, the horizontal reflection plane is always 90 degrees to it. And so you put that highest order axis up and down, and then the plane is horizontal to that. And this is not a planar molecule. It's those nitrogen-hydrogen bonds go down below that plane. So it does not have a flat plane of symmetry. So we're going to say no to that one. And does this molecule contain 3 vertical planes? So if I'm looking at the NH that's in the screen, notice the wedge hydrogen and the dash hydrogen reflect into each other. So that is a reflection plane. And in fact, the NH coming out of the screen, the back hydrogens will reflect into each other. And the one that goes into the back hydrogen, the front hydrogens would reflect into each other. So it has 3 reflection planes. And they're vertical. They contain that vertical symmetry axis. And so absolutely yes on this one. So you determined the point group to be C3V. So if you'll notice on your flowchart, that's where we arrived. We went through all of the questions. We ended up down in this middle part right here where it says CNV. N is 3 for our molecule. Once you determine N, it's N for the whole page for that. So we got up there, we found a C3 axis, and then it's going to be C3V when you get down to the bottom. So that's how you use the flowchart. And then it says check your answers, okay? So come up here, and it turns them all green. If we had made a mistake, there'd be a red one and an explanation as to what we screwed up. So that's really cool. All right, so does this molecule contain 2 or more unique C3 axes? Show, okay? It shows that there's 1. Okay, so that's the C3 axis. And then we can play the rotation around that axis. So play it. Okay, so that's the C3 rotation. Okay. Select the highest order. Okay, show it. We've got that. Play. Okay, we've got that. All right. Now, does it contain 3 vertical planes? Now, the difference between vertical and horizontal planes, the vertical ones contain that axis. So I'm going to hit show. You see how they all contain that vertical axis. Okay. And it says play. So I'm going to hit play. So it's showing, that just showed one of them, I guess. Okay. And that's it. Those are the symmetry elements that ammonia possesses. Reflection planes and the C3 axis. Okay, now you get to choose. Which of these molecules, if you can read over here, do you want to do next? Or if there's one that you know of, we can find it on the list. There's a lot of inorganic compounds. We probably shouldn't do anything too complicated just yet. Okay, let's do water. Okay, it's a classic. Okay, so here's water, how we draw it on the paper. Everything's in the plane of the paper. Does it have an infinite rotation axis? Again, is it linear? No, it's not. Okay. What if I hit yes? Let's go. Oh, I can't. Okay. Does this molecule contain 2 or more unique C3 axes? I'm going to screw up and say yes. Okay. All right. Oh, gosh. Yes. Okay. Does this have it? Yes. Okay. So I determined that this is a IH. So I went through the flow chart and it let me get to IH. Okay. So it looks like I did great. Check answers. Okay. So it says incorrect. This molecule does not contain any C3 axes. Okay, and then it just goes down and says incorrect, incorrect, incorrect. Okay. So let's come back up here and hit, let's see, how do I reset? You see reset anywhere? Let's just go down here and click water. Okay. All right, so here's water. Does it contain an infinite rotation axis? No. 2 or more unique C3s? No, it doesn't have any threefold symmetry. You got to have at least 3 of the same kind of atom to have threefold symmetry. You can write that down. Okay, if it doesn't have something 3 in H3 or whatever, then it can't have threefold symmetry. Okay, so select the highest order proper rotation axis if there are any. Do we see any rotation axes? Is there any way I can rotate the molecule where it will come back to me? Twofold, yeah. So if I rotate it around the oxygen, then absolutely. So twofold, select. Okay. Then it's asking, are there any perpendicular to the axes to that? So I wish I could annotate my screen. If this is where the axis goes up and down. Okay, so that's the vertical axis, and a horizontal axis would take those hydrogens and rotate them up. And there's no hydrogens up there to rotate into. Okay, so we can't have any perpendicular rotation axes if we don't have hydrogens on top of the molecule that this could rotate into. Okay, so we'll say no. So that throws us into the C groups and keeps us out of the D groups. If you look on here, that's the question that separates C versus D. So it says, identify the highest order CN. Are there N perpendicular C2 axes? We said no. So now we're down here at the below. We're like CNH, CNV, or CN, or S2N. If we said yes, we'd be over there in the D groups. D and H, D and D, or just DN. Does this molecule contain a horizontal reflection plane? Again, that would be the plane that's 90 degrees to that symmetry axis. We say no. Does it contain 2 vertical planes? And there's one that goes this way where the hydrogens reflect into each other. And then if it's a planar molecule, the plane of the molecule is always a reflection plane. So this molecule is planar, it's just bent, but it's bent and it sits on the plane. And so the tops of the atoms can reflect into the bottoms of the atoms. And so it does have a 2 vertical reflection planes. So we say yes to that. And we've determined the point group to be C2V. Check answers. So yes. So up here is our rotational axis, our C2 axis. We can play that. That's the C2 rotation. And then we have our reflection planes. And they can reflect into each other. It looks like that was the same as the rotation, but it's not. See, this is a reflection. You see that? And then this is the rotation. Okay. So those are all of the symmetry elements for water. You have the identity symmetry element, the rotational axis, and both planes. So there's 4 in water. Let's do one of those D groups, right, where we say yes to that really confusing question. So let's go up here. Let's do staggered ethane. Okay. So we're going to draw the molecule like this, where we have the carbons and 2 of the hydrogens in the plane, and then we're going to have a wedge coming out here and a dash going in the back, and a wedge coming down here and a dash going in the back. Okay, so that's our ethane molecule that's staggered. You understand what staggered means? It's the methyl groups are rotated against each other so that they're in between. Okay, so does it have a C infinity axis? No, that would mean it was linear. Does it contain 2 or more unique C3s? Well, I've got a C3 going through the carbons, but that's it. Look at the molecule, try to convince yourself, you can't find any other threefold axes. So we're going to say no. So we do have a C3 axis, so we're going to pick 3 here and hit select. So this C3 axis goes through the carbons. But look at the plane of the board. Like, look at that molecule, the axis coming right out of the molecule. So right here is a C2 axis. You see that? That C2 axis right there going through the center of mass of the molecule, and all the axes have to go through the center of mass. So that's another way to find them, is you can't have an axis here because that carbon is not the center of mass of the molecule. The axes have to go through the center of mass. And so right there is a perpendicular axis. This hydrogen will rotate into the top one. Okay. And this front hydrogen will rotate into the front hydrogen on the top. And this back hydrogen will rotate into the back hydrogen on the top. So that's a C2 axis. And because this has threefold symmetry, there's 2 more. Okay. They're just more difficult to see because they don't line up with the plane of the paper or anything like that. But there are 3 C2 axes. And when you do this lab next week, you'll have the model kit, and you can rotate it around and turn it and rotate it. And if you want to bring tape and toothpicks or whatever, do whatever you can so that you can see the symmetries. Okay, so that there definitely are 3 C2 axes perpendicular to the C3. So we'll say yes to that. And then later it'll say show, and we can show them. Now, does this molecule contain a horizontal reflection plane? So the principal symmetry axis is vertical. So the reflection plane would be horizontal to that. And this hydrogen down here has nothing to reflect into. So we would say no to that one. Does this molecule contain 3 dihedral reflection planes? So look at the plane of the paper, right? This front hydrogen can reflect into the back, and this front hydrogen can reflect into the back. So the plane of the paper is a reflection plane, a vertical reflection plane. And there's 3 of those. So if I have one for this hydrogen that contains that hydrogen, I also have a reflection plane that contains this one and a reflection plane that contains that one. And so I have 3 vertical reflection planes, and so we'll say yes to that one. So you've determined the point group to be D3D. And all of your staggered molecules will have that D on the end. So if it's like ferrocene, where you have 5-membered rings on top and bottom of an iron and they're staggered, then it would be D5D. And if it's ethane with methyl groups, it's D3D. Alene is a really tough molecule to see. We can do that next. It has 2-fold symmetry, and it ends up being D2D. It's staggered, and it's a D group, and it's a D2D. So let's check our answers. So here's our symmetry axis, the C3 axis. We can play that and see the rotation. Okay. Here's the 3 C2s. So we looked at the one that's coming straight at us. But look, here's 1, 2. And here's 1 as well. So we have 3 C2 axes that are perpendicular to the C3. Look at where they go. It's kind of confusing. They don't line up with the plane of any of the bonds. Okay, they kind of break the bonds. They go in between the bonds. So those are your 3 C2s perpendicular to the C3. And we had it drawn like this, and we could see that, coming straight out of the paper was one of the C2s. If we were then to rotate the molecule, a third of a turn, then we would see that one, and another third of a turn, we would see that one. Okay. So let me just animate one of those. Let's see which one we get. Okay, that's the C3. And here's the C2. Okay, let me rotate it this way. Okay, so this is the C2. It's not going to let me do that. Anyway, strange. Okay, so then what about the reflection planes? Here are the 3 reflection planes. And again, they contain those bonds. We'll play one of those. Yeah, you see. So those are all of the symmetry elements in ethane, staggered ethane. Let's do one more. Let's do kind of an easy one here, chloromethane. Okay. First of all, we've already determined ammonia to be what? What was the point group of ammonia? C3V. If you look at this molecule, eventually my goal is for you to look at this molecule and say it's no different than ammonia from a symmetry perspective. What did ammonia have on top? It had a lone pair. So it had a thing on top that was unique and 3 hydrogens. This has a chlorine on top and 3 hydrogens. So if you take that chlorine off and put a lone pair there, it's ammonia. It's got a carbon atom. But again, this is symmetry we're talking about. We're not really talking about chemistry yet. We're just looking at the symmetry of the molecule. And so let's go through this. It does not have a C infinity axis. It doesn't contain more than 2 or more C3s. We're going to pick that C3 axis going up and down. Are there 3 C2s perpendicular to it? No. Does it contain a horizontal reflection plane that would be across the, left to right? No. Does it contain 3 vertical planes? Yes. Okay, so we're going to have those 3 mirror planes that go through that carbon-chlorine bond. Yes. You've determined the point group to be C3V. Same answers to the questions that we had for ammonia. Check our answers. We could play some of the things. Here's their rotation. Here's the reflection. We could show those symmetry elements. So what I would like for you to do is get familiar with the flowchart. You'll have the flowchart on the exam, so you can use it, okay? But eventually, I would like for you to wean yourself off of the flowchart by having classic molecules in your head, knowing that ammonia is C3V. And then you look at a new molecule and you go, that looks a lot like ammonia. So that molecule is C3V as well. Okay. Or water. Water's a classic C2V molecule. So if the left and right look the same, the front and back look the same, but the top and bottom look different, it's C2V. Okay. So now let's go back to the lecture and talk about why we care about point groups. So let's assign the point group for this particle in a 1D box wave functions. We looked at the symmetry last time of even and odd, but now we can look at the symmetry elements. We have identity. Everything has the identity operation, and these characters in front of our wave functions after we operate on them are these things right here. These characters right here. And so some wave functions are going to be on the top row, fully symmetric. Last time we were calling those even. And other wave functions are going to be on this other row, and that's called odd. Okay. And now we have this idea of this character table. Okay, can I have you pass these out? These character tables have all of the symmetries of all the different kinds of wave functions you can have in a molecule, and all of its motions, its rotations, its vibrations, and everything. And so once you find the point group, you can find the character table, and then the character table has all of the actions that molecule can do. So here we have for this particle in the 1D box the character table. For Ci, that's the point group of this molecule or this system. Particle in a 1D box is Ci. we only have one dimension, and all we can really do to that is either nothing, which is the identity, or invert it. That's all. So those are the only two things we can do to our 1D wave function, and the only point group that has E and I for its symmetry elements is CI point group. Okay. And so we can now, instead of just labeling our wave functions even and odd, we can use these AG, AU, AG labels. And so these labels right here are called Mulliken notations. Yes?
So if we're having to write down the point group and the character tables, would we have to do like CIAG when we're like labeling them?
No, we would label the molecule CI, and then we would know that all of the other labels are within that character table. So once you identify the point group, so if you look on here, there's some really big ones, like D2H right there on the front top. Look at all of the Mulliken labels we have for that. You know, AG, B1G, B2G, and everything. This is really quite complicated. So once you've identified the point group, then everything from that point on is inside that character table. Yeah. And again, you'll have the character tables too on the exam to answer your questions and so on. So you don't have to bring this to the exam. You can bring your note card, and I'll provide anything big like this. It's mainly in teaching you how to use this, and I'll show you why we're going to benefit from this. So that top row is the only even row. All other rows are odd. And so let's do our selection rules. We got lots of handouts today. You give everybody a Post-it note. Okay. I'll just break them into pieces here. Just to emphasize the benefit of symmetry. Having you determine the selection rules that we did from the calculus lab, and having you do it on Post-it notes compared to your 6 pages of calculus. Okay. This is getting harder though as people start using electronic devices. One time recently, I think it was last spring, we needed to write something down and nobody in class had an actual pen with ink in it, you know, that you could write on something. So it's kind of strange. And so what we're going to do is we're going to say, I'm just going to change this one here from say n equals 1. So we're going to say n equals 1, that's AG, to, let me do this. Okay. And X. And I'm going to say, so to 1 plus delta n when delta n is equal to plus or minus 3, plus or minus 1, 3 plus or minus 5, ... Okay, so we're calculating the jumps from n equals 1, which is AG, using light, okay, and going to 1 plus delta n when delta n is 1, 3, 5, etc. So what does that mean? So when delta n is 1, we go to n equals 2, and that's AU. When delta n is 3, we go from 1 to 2, 3, 4, and that's AU. So I'm picking up all of the AUs. If delta n was 5, we go from 1 to 6, right? And the 6 would be AU. So all of those up here, when delta n is 1, 3, 5, would be AU. Okay. And then light, we need to find light in our character table. So here's our character table down here. And X is, in our system, X is AU. So this is light. And so AU here in the middle. So this is our transition dipole moment symmetry setup. Okay, let me just clean it up. So we have AU times AU times AG. Now we need to know how these rows, when I multiply AG times AG, I'm taking 1 times 1 and 1 times 1, and I end up with positive 1. So AG times AG is AG. But what if I take AG times AU? I have this 1 times 1 equals 1, and then I have 1 times minus 1 equals minus 1. So I could go in and I could figure out how all of these rows multiply by each other, what other rows they give me. That's the thing about group theory. If I multiply 2 rows, I get another row in the character table. So I'm never going to get a row that's out of the character table. If I multiply 2 rows, then it's going to be some combination of rows in the character table. And so here's what we call the direct product table. And it tells us how all of the rows multiply by each other. So if I want to simplify this, and on your post-it note, you can draw this, AU times AG. I come down here and I find AU times AG. And that's my result right here, AU. It's the same as even and odd, okay, that we did last time, but it's just using the correct notations now. So this one comes down here. And now this is the last one, AU times AU. So now I have AU times AU. So I find that in the table, and it's AG. And AG is my top row. So an integral over all space of a wave function or integrand that is top row is not equal to 0. So I've just solved for the selection rules, or shown that delta n plus minus 1, 3, 5, 7, all of those are allowed by symmetry. If we were to do 1 x and then 1 plus delta n, when delta n is equal to plus or minus 2, 4, 6, etc. Okay. Then I still have AG for the ground state, AU for light. And then looking at changing by 2, I'm going from 1 to 3, that's AG. Changing by 4, I'm going up to n equals 5, which would be AG, etc. So those would all be AG. So I can look at this integral, and I can do the symmetries, these direct products. So AU times AG is AU. I bring this one down. AG times AU is AU. And so that's an integral over all space of a function that's not the top row. So not top row. So this one is equal to 0. So I've now figured out that all of the even jumps in quantum numbers are forbidden by symmetry. Think about that. Compare that to your calculus that you did. I mean, all those pages of math to figure out that the integral was 0. Okay, and now we know from the very beginning that those 3 functions times each other when integrated over all space are going to be 0. So that's why we like symmetry. When they did it for the particle in a box, we could do it for benzene, we could do it for everything. So these are the character tables. Let me just show you, we're just going to sort of fly through the next few slides. Here's all of the ones I gave you. There's lots and lots of different Mulliken notations, different symmetries of the wave functions and motions of the molecule. But the thing is, in every character table, the only even row is the top row. So that's why I didn't say AG, I said top row. Sometimes you don't have G's and U's, you just have A1s. And so I can't say it has to be AG or it's non-zero because there may not be an AG in that whole molecule. Maybe it's just A1. Maybe it's just A prime, okay? So an integral of an even function is non-zero. Integral of an odd function is 0. And we have those multiplication rules, which we get from the direct product tables. So here's our character table. That top one has even symmetry. All of the other rows have odd symmetry. This top left piece is the Schonflies notation. That's the point group for that character table. And these are Mulliken notations. We also call those irreducible representations. So in a linear algebra way of thinking about it, each row is linearly independent from the others. Okay, and if they were able to be a combination of others, then they could be reduced. And so these are irreducible. They're the lowest order, I guess, of the different kinds of rows that you can have. These plus ones and minus ones, and there'll be other characters and other character tables. Those are the characters. Those are how the wave function or the motion of the molecule behaves under that symmetry element. And then we could take these Cartesian and rotational basis functions through the character table and see what it does under reflection or rotation, and it would be able to assign a particular row. They've already done that for you and put those functions over here on the right. And so when we're trying to figure out how light interacts with a molecule that has a C2V symmetry, this tells us that light polarized along the z-axis would come in with A1 symmetry. Light polarized along the x-axis of this molecule would come in as B1 symmetry. So it would interact with other kinds of things. Like if you have a vibration that's a B1 and light's coming in as a B1, they'll interact. If you have light coming in with a A1 and you have a vibration that's a B1, they're not going to interact. Okay. And so this is just some information about those character tables. We have the Mulliken notation. Some of the letters mean something. So like it's an A if the character under its rotation is a +1. It's a B if the character under that rotation is a -1. We have two-dimensional rows, and those are labeled E. And I'm sorry, but there's nothing I can do about that. We have an E that is a symmetry element, which is the identity operator. And then we have an E that is a Mulliken notation. Okay. Context. This is on the same table. I mean, I could like wring their necks for doing that to you guys, but hey, I'm not going to like change that because then you won't understand what you read in the literature. And so I'm teaching you how it actually is, and the notation is kind of crazy. So we have E's everywhere. We have E for energy. We have E, which is now the identity element, the do-nothing element. And we have E, which is a two-dimensional Mulliken notation. Then we have subscripts G's and U's if there's an inversion center. And so if we notice up here, there's an inversion operation here, and the +1s, or the positive characters are G's, and the negative characters are U's. And so we would say these are symmetric under inversion, and down here we would say these are asymmetric under inversion. And that's it, 8:50, we did it. Okay.